So guys, welcome all, a warm welcome again to Mercy Technologies. Let me start from the place again. So what we have done till now is we have filled up half of what we achieved to fill till now. So in an iterative approach, the factorial's time complexity is order of n, and the recursive time complexity is order of n. The space complexity of iterative is order of 1. The recursive approach, the space complexity is order of n. By this, what we have concluded was we have concluded that recursive is not as good as iterative, right? Let me open up what we have filled up till now. So we have filled up the first table. This is the factorial. Since the recursive is taking the space complexity of order of n, we have concluded that iterative is a better approach. But as I have mentioned previously, there is one thing called memoization. There is a concept called memoization, right? There's a concept called memoization. Using memoization, you can reduce the time complexity, right? You can reduce the space complexity, but I cannot cover that right now, but we'll be doing that in our master course. Right now, let's come back to the Fibonacci series. What is Fibonacci series? Let's go back and try to understand what is Fibonacci series. Let me clear off everything. Let me clear off everything. Let me import it. Okay, so this is Fibonacci series, guys. This is Fibonacci series. So what it says, Fibonacci series starts from 0, and what is the next number? It starts from 0 and 1. It starts from 0 and 1. What is the next number? 0 plus 1 is equal to 1. And now 1 plus 1 is equal to 2. And 1 plus 2 is equal to 3. 2 plus 3 is equal to 5. 3 plus 5 is equal to 8. 8 plus 5 is equal to 13. So on and so forth. So this is what the illustration of it is. So it starts from sum. These are the first initial conditions. These are the two conditions, and from that it moves forward like what we have in the illustration. So I think you understood. So what is the Fibonacci series? Fibonacci series starts from 0. It starts next as 1, and after that you sum up the previous two numbers, and the next number will become that. The previous two numbers, next number will become that, so on and so forth. So this is Fibonacci series. So guys, I think you might be having a pen and paper with you. So maybe this you might have learned in your first or second year of your computer science courses, or the people who are already attending. This is I don't say it's a very important interview question, but this is the base for all the interview questions that are asked, and this is the base for calculating space and time complexity, right? If you have a chance, it is a 2 lines or 3 lines, maybe a 4 lines code. If you have a pen and paper, you can start writing program for Fibonacci series. You can start writing program for Fibonacci series and try to brush up on where you remember. After that, we'll go straight away into the program. I'll give you just 2 minutes, guys. Start writing it. Okay. Now we have this diagram over here. Our program's requirement is we need to write a program for Fibonacci series. I think people will be writing program on your notes with a pen and paper. Let me not waste more time of yours. I see people. Okay, one person has replied me. Good. Okay, so let me show the code directly. Fibonacci series, we need to find out in two different approaches. One is iterative and the second is a recursive. What is an iterative approach? So this is the iterative approach. So what we have written, there is a method, main method. Let's not think about it right now. So there is an iterative method, and here we have a program. We have taken three variables a, b, and c, and after that we are trying to print the a and b value. These are the initial values. If you remember, 0 and 1. If you see, these are the initial values, 0 and 1, and after that we started iterating over a for loop. We are trying to write all our logic over here and trying to print the next number, and we are moving forward. So let me, this is a very simple program. So we have taken two values, which is the initial values, and the c will be the value that comes by summing a and b. Let me try to run this program, and I have given the input as 7. Okay, let me try to run this program. Okay, 0 1 2 3 5 8 13 21 34. So this is what is coming here, 21 34, right? As we improve or as we increase our input, the number increases, and that is how the Fibonacci series gets formed, right? The reason why you see this red color and green color is like I have enabled the JUnit test, guys, so don't mind. That's not our requirement to learn right now. So we are able to see that there's a proper output coming out of this Fibonacci series program. Now let's try to find out one thing. So what is the time and space complexity of this particular program, right? This is the actual logic. Let me go back to the whiteboard. I'll try to create a new slide, paste the code for you. I'm pasting the code for you, right? This is our actual code. This is our actual code. So what we are trying to do over here, let me remove that so that it will not create a problem for you. Okay, so what we are trying to do over here is we are iterating over the input. Here we are trying to iterate over the input. So what happens? What is the time complexity? What is the time complexity? What is the formula for time complexity? Formula for time complexity in terms of iteration is the number of steps in terms of n, number of steps in terms of n, where what we are doing for I is equal to 1, I less than or equal to n, I plus plus. So what we are doing for n input, we are iterating it n times. For 10 times, we are iterating it 10 times. For 15 times, we are iterating it 15 times, right? So what happens? So because of that, what we can conclude, the input, the number of iterations are equal to n. So what is our conclusion? Our conclusion would be, in iterative approach, the time complexity is order of n, right? The time complexity is order of n. I think you're clear with this, with the calculation, and this is the formula for it. Now let's try to find the time complexity in terms of recursion. So what the recursion formula says, number of recursive calls into time complexity of each call, and we are ignoring the recursive call, right? Number of recursive calls into time complexity of each call. Let's try to understand how many recursive calls are there in this particular program. So let me try to see number of calls that are there. What I'm trying to do here, I'm taking the input is equal to 4. Let's say the input is 4. How many calls will be there? Initially there'll be a call f of 4, and what this does, it, sorry, so let me paste the code for recursive approach. Okay, I'll show you what is the recursive approach. Recursive approach, what is this recursive approach saying? Recursive approach is saying that this is the base condition, this is the base condition, this is also the base condition, these two are the base conditions, and what are we trying to return is, we are trying to return Fibonacci of n minus 1 plus Fibonacci of n minus 2, right? we are trying to return Fibonacci of n minus 1 plus Fibonacci of n minus 2. So these two are the recursive calls, guys. There are two recursive calls, right? For every call of this method, there are two recursive calls, right? So if we run this program, we'll be getting the similar output for what we got for an iterative program. So this is very simple. Let me try to put this code into our whiteboard and try to understand how to calculate the space and time complexity for this. Let me remove everything. Okay. So I'm pasting the code so that we can analyze it. Yeah, here what we are doing over here. So we are trying to analyze this Fibonacci series code. This is a base condition 1. This is a base condition 1. This is base condition 2. Okay, and this is the Fibonacci series n minus 1, Fibonacci series n minus 2. What is this? There are two recursive calls in our program. As we see in Eclipse, there are two recursive calls on line number 11. So what I'm trying to do, I'm trying to take an input is equal to 4. So when you try to take the input is equal to 4, let me try to show you how many method calls happen. So f of 4, what is it trying to do on this part? It is calling f of n minus 1, which is f of 3, and again it is calling f of 2. And what is f of 3 calling? F of 3 is calling f of 2 and f of 1, right? F of 2 is in turns calling f of 1 and f of 0, right? But what is f of 1 calling? F of 1, it's not calling anything. It's not calling. The reason is it is coming to this base condition 1, right? It is not calling anything. And now what is f of 2 doing? F of 2 again calls 2. What is that? F of 1 and f of 0, right? So what happens? These are the method calls that are happening internally. So for input n is equal to 4, how many method calls are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. But here one thing that I want to say is because of our base conditions, we are not calling for these, right? But this is because of the program that we have written. But let's say even those are there. What happens? There will be two more calls. So what is the total number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So total is equal to 15. So when the n is equal to 4, number of method calls are 15. Let's say it is equivalent to 16. So which means when n is equal to 4, method calls are 16, which means the method calls are directly equivalent to 2 power n. Right, the method calls are equivalent to 2 power n. 2 power n in the sense 2 power 4 is equal to 2 into 2 into 2 into 2, which is 16. So the method calls are 16 for the input, which is 4. You take the input as 5, you'll be getting 2 power 5, which is 32. You try to calculate, or you try to have a table like this. What are the method calls that it's trying to achieve? And you will come to know that the number of method calls are 32, right? So based on this, what we conclude is the time complexity is, what is the time complexity formula? Time complexity formula is number of recursive calls into time complexity of each call. Number of recursive calls, how many number of recursive calls? Number of recursive calls are 2 power n, right? 2 power n. Time complexity of each call is order of 1, guys. We are not trying to do anything over there. So at the end, based on our formula, what are we trying to achieve? What are we trying to conclude is the time complexity of Fibonacci series with the code that I have written right now is 2 power n. So which means order of 2 power n, right? And this order of 2 power n is a too big number, right? Your input is 4 and the method calls are 16. Your input is 5 and the method calls are 32. Your input is 6 and the method calls are 64, which means it is increasing at the order of 2 power n, which is not a good time complexity, right? Let us try to fill the same table over here. What is time complexity? Order of 2 power n. So with this only we are able to conclude that in Fibonacci series, iterative approach is better than recursive approach. The reason iterative approach is having a time complexity of order of n, and recursive approach is having a time complexity of 2 power n. Now, let's even move to space complexity. Even though it is not needed, we have already made our conclusion. But even then, I want to explain about the space complexity as well. There is place, like how did we calculate? We have taken a stack, we have calculated the stack size and all, right? So we'll be doing that now. So before that, guys, I just wanted to know if you guys have understood the time complexity calculation in terms of recursive or Fibonacci series. Please reply me so that I'll conclude that you are following me. Please reply. I just want your acknowledgement, guys, so that I can move forward. You can reply me in WhatsApp. Okay, perfect. I'm able to hear. I'm able to hear from people. Good, 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 good. Okay, okay, great. Okay, great. Okay. Yeah, fine. So I think people have understood how I have calculated the time complexity to be 2 power n. Now let's conclude our session by calculating the space complexity. Let's try to calculate the space complexity of Fibonacci series in terms of in terms of iterative approach. So what is the formula? Extra space in terms of n. What is the extra space that you are taking in this code? Are you taking, so this is the recursive approach, right? We are trying to do that. And now the space complexity we are trying to do in iterative is iterative one. Yeah, iterative one. So what is the extra space that you are taking for this for loop in this method? The extra space that you're taking is nothing. There's no extra space. There's no array inside it. There's no hash map. There's no array list. It's not increasing with the input that you're giving. So what is the conclusion? The conclusion is the space complexity is order of 1. The space complexity is order of 1. It's not taking any extra space. The code that we have written is not taking any extra space. This is the method, and this method is not consuming any extra space. So the space complexity is order of 1. So final conclusion, what is, just a second. I think somebody has messaged me something. Okay, so what is the space complexity, guys? Let's try to wrap up by calculating the space complexity. Space complexity, how do we calculate? What is the formula for the space complexity for recursive is maximum length of the stack into space complexity of each call. We are ignoring the recursive call. Let's try to find out with the same code. With the same code, right? So I'm copying it. Let me paste it in a new slide, right? Let me make it as compact as possible. As compact as possible. Okay, so what we are doing over here, we have our code right now over here, and we are trying to find out the space complexity. To find the space complexity, we need to find out the maximum stack size, maximum length of the stack, as we see in the recursive space complexity formula. So how do we calculate? First, like, let's try to understand. I'm taking the input n is equal to 4. N is equal to 4. So when n is equal to 4, what are the number of method calls? F of 4, it is calling f of 3, and in turn it is calling f of 2. This is calling f of 2, f of 1, f of 1, f of 0, f of 1, and f of 0. So this is what we have concluded while we were calculating the time complexity. Now let's try to understand what is the kind of a stack that is getting created internally in the memory. Let me try to draw the stack for you. Okay, so what is the first method that loads? First method that loads is f of 4, and then it comes to f of 3, then it comes to f of 2, then it comes to f of 1. What happens after that? F of 1's calculation is over. Now this is the stack, this is the top of the stack. So when we are removing this top, the insertion again goes on the top. So what happens? This area is now free. Now we are trying to load f of 0. So what happens? We are trying to load f of 0. So this f of 0, even now the f of 0's calculation is done. Let's try to remove that. As I previously told you, these are called as activation records, and this is our stack. Now f of 0 is done. Now the control is in the f of 2. F of 2 is here. F of 2's calculation is done because nothing is there inside it. Now we are going back to f of 3. This is f of 3. This is f of 3. F of 3 is in turn calling f of 1. In turn calling f of 1. When we are having the f of 1, the f of 1's execution is done. I'm removing f of 1. I'm coming back to f of 3. F of 3's execution is done. We came back to f of 4 now. F of 4 is here. F of 4 is calling f of 2 in turn. F of 2. So what is f of 2 doing? F of 2 is now internally calling f of 1. F of 1. So f of 1's execution is done. I'm removing this. Now it's coming back to f of 2. It's coming back here. Again, it's calling f of 1, f of 0. Okay. Now this execution is done. This activation record is also gone. Now the control came back to f of 2. F of 2's execution is done. Its activation record is destroyed. Now f of 4 has come. The activation record is destroyed. And finally, the stack is going to get destroyed. Right? So what happens with this? What we are trying to achieve is we try to find out what is the height of this stack. What is the height of this stack? Height of the stack is 1, 2, 3, 4. Right? So height of the stack is what? Height of the stack is 1, 2, 3, 4, which is 4. So when the input is 4, the height of the stack is 4. When the input is 5, the height of the stack is 5. When the input is 6, height of the stack is 6. You can try to find out or try to draw the similar diagram and find it out. The height of the stack is directly proportional to n, right? Which means what is the conclusion? In the formula that we wanted to highlight, we need to find the max stack, max length of the stack, and the input of this, when the input that we are giving is n, then max length of stack is n. So which means, and then space complexity of each call. Space complexity of each call, we are not trying to do anything in this Fibonacci. We are not trying to create any array over here. So that is why the space complexity of each call is order of 1. Order of 1 into order of n is equal to order of n. We are ignoring the recursive call. Finally, we conclude that the space complexity is coming to be order of n. Let's try to fill it in the same table. Let's try to fill it in the same table. So what is it? Order of n. Guys, we have done the conclusion here. So what is it? Since the space complexity is more, since the time complexity is more, using an iterative approach is better when we are trying to calculate the Fibonacci series. I think you're clear with the calculation that I made. But the important point to hear about, again, I'm trying to tell you the same thing. So we have written the program in this way. We can improve the program so that the recursion becomes better using a concept called memoization. Okay, this is an important point, guys. We can cover that in our master course. But I think by this time you are able to calculate space or time complexity of any loop or any program that is giving to you using these formulae. You can take a screenshot of this and keep it to you for your ready reference. Anytime any code that is given to you, you can calculate the space and time complexity. And one more thing, guys, when you find out that the time or space complexity is getting more, you should be in a position to identify that and make corrections in the code so that your code becomes better and clean. With that, guys, we are trying to end up our session, and we are concluding that iterative approach is better than recursive approach in terms of space and time complexity. But there are ways to improve writing code in recursive using a concept. Not just this, there are many other concepts. People expect all these from you when you are going for an interview. When you are clear with all these basic things, guys, believe me, you'll be getting a very good job in a very good product based company.